Okay, welcome everybody to the last year's talk of the Seminario de Álgebra, Combinatoria, Teoría del I de la Universidad Nacional del Sur. It's a great pleasure to introduce Gaëtan Borot from Humboldt-Universität from Berlin that will talk about Airy structures from algebra to geometry via representation theory. Thank you, Gaëtan.
So thank you very much, Fiorella and Emilio, for the invitation. It's in fact the first time I'm in Argentina in some way. So I want to start by introducing what are Airy structures. And then I will try to explain why they're interesting, at least why I'm interested into it. So let's start with a vector space V. We'll work over C. And I want to consider the algebra of differential operators on V. So there will be some variables xi and some derivation d0 dxi. But somehow I want these generators, I want to multiply this by an h bar, which is a formal parameter. And then I work over the ring of formal power series in h bar as well. So it's the ring generated by this, where xi is a basis of linear forms. And of course, divided by the relations that h bar d0 dxi commuted with xj should be h bar delta ij. So this is a graded algebra with the following convention for degrees. So xi, I put them in degree 1, and h bar, I put it in degree 2, so that the degree of h bar d0 dxi is effectively, so 2 minus 1, that's effectively 1. And so now I can define what are Airy structures. So an Airy structure, AS, is a linear map, L, from the vector space V to the differential operators.
Gaëtan, can I ask you something?
Yes.
In the definition above, is there any distinguishing operator like a Laplacian or?
The Laplacian will be in there if you want.
Okay.
It will be an element in there.
Okay, thank you.
I consider operators of any degree, non-negative degree, maybe not homogeneous.
And it has degree 2, right? That Laplacian?
So the Laplacian, if I write it like this, is going to have degree 2 indeed.
Okay, thank you.
So an Airy structure is a collection of differential operators, one for each element of the basis of V, which satisfy two conditions. The first one is that these should stack like h bar d/r dv, the derivation in direction V. So that thing is of order 1, and all the rest is of order at most 2, which means there's no degree 0 term, and the only degree 1 term is this derivation with respect to V. So I call that the degree 1 condition.
So this is about the total degree, no the h bar degree.
So h bar is included in, so I give h bar a degree 2.
But
So,
I mean,
for example,
you don't mean that this is h squared plus something or times something.
I mean that
it's
here you would
only
have
a
terms
degree
of the
2.
form xx.
Xx is okay.
That's xx is degree 2. H bar alone as a constant is degree 2. Or if I have, I don't know, xd as degree 2. But I could also have something of higher degree with many x's.
Yeah, okay, thank you.
And the second condition that whenever I commute two of these operators, I should get something which up to a constant h bar is in the left ideal generated by the differential operators that we have. So it's a sort of compatibility condition. I will call that a graded ideal condition. So this is a family of differential operators, which are perturbations of the trivial, just of the derivation, and which are compatible in the sense of two. And it's a fact. This dates back to Kontsevich and Soibelman. That you can find a common solution to all these differential equations. So there exists a unique F, which is a power series in h bar. It's only, it can start with 1 over h bar, but otherwise it's a power series. There's no constant terms. And so the FGNs are the Taylor coefficient of this. You can think of it as a formal function on V. Such that well, this is killed, exponential of f is killed by all the operators you have in your Airy structure. And there's a normalization which makes uniqueness that you don't want F01 and you don't want F02. So it means this F, the first term that you may have is an h bar to the 0 x and an h bar to the -1 xxx plus higher order. So this exponential of f that you can attach to an Airy structure, it's called the partition function. And so that's what you want to compute. That's the solution of all these equations. If you took an arbitrary collection of PDEs, in general, there wouldn't be a common solution. And the fact that here we have existence really come from this condition 2, which is more or less stating that these operators are compatible. Whereas the condition 1 is responsible for the uniqueness of the solution. So there's an easy way, well, it's a systematic way to compute this solution. And this is obtained by the so-called topological recursion. Which is a recursion on 2g minus 2 plus n. So we compute these FGNs by a recursion on 2g minus 2 plus n. And it's called topological because, well, 2g minus 2 plus n, it makes you think of the Euler characteristic of minus the Euler characteristic of a surface of genus G with n boundaries. And indeed, the recursion really looks like chopping off surfaces. So I'm going to write what the recursion looks like graphically. So let us represent whenever I have a certain number m of x's, a certain number of differential operators and an extra power of h bar. It is represented graphically in the following way. So the linear forms come from the top, and the derivation, which are like vectors in V, are at the bottom. And here there is a certain G, which I want to think of the genus of this box. So when I write my linear map L, it contains this. So there's V, which is incoming here. And it goes through a box and produces a derivation, which is just the h bar dv. So here's h bar, h bar. So this is the identity. That's the first term we have. And then there's all the rest. So all the rest is going to be a sum of many things of this type. There's always a V inserted, and then these are the XXX, h bar d, h bar d. And there's a sum of terms like this. So now if I want to compute what is FGN, so FGN, it's the Taylor Taylor coefficient. So we have to represent it as a box like this. So there's n x's, n of them, and inside is a certain genus G. And if we translate this equation here, it gives the following recursion, where this is equal to take any of these boxes coming from the coefficients of the operator LV and connect it to a lower f. That's why I write it in pink. So in white, these are coming from these are the operators coming from the coefficients of LV. And in pink, that's the f's. And because there's many possible white boxes, it's a sum of such things. But the fact that all of these are degree at most 2 makes that the box that we have here, it's a certain f g prime n prime with 2g prime minus 2 plus n prime smaller than 2g minus 2 plus n. And so this is a recursion. So let me write the first term that we have. And I'm going to, instead of writing these lines, I'm going to thicken that and make it look like surfaces. So we have something like this. That can connect to something like this. And so here there's a genus G. In what I wrote, I had G prime plus J prime prime plus. And it was K of these guys, K minus 1 is equal to G. So here I'm having a genus 0 on the white guy. So this is something that connects to an FGN minus 1. But I may also have terms of this type. And here, there's a genus in the middle here. So this guy will have genus G minus 1. So that the total thing has genus G. And there's many other terms. But what we notice on this picture is that the terms are in one-to-one correspondence with sub, or let's say embedded so embeddings of surfaces, sigma G prime inside is sigma Gn. So sigma Gn is a surface of genus G with n boundaries, which are labeled, such that the first boundary of the embedded surface is the same as the first boundary of Gn, that this guy here. And I want such things so that sigma minus the image of phi has negative Euler characteristics. So I don't want cylinders or disks when I remove it. And I want to consider that up to diffeomorphisms.
Gaetan,
Yeah.
for the glue pants at the right, could you say again why the genus is G minus 1?
So here, when I connect, you see that there's a handle in the middle. So when I connect these two surfaces, if I have a genus G minus 1 here, I'm going to create another handle. Therefore, the total thing will be genus G.
Okay. Sorry.
The reason, so why it works like this, so far it's an act of fate, but I'm saying this comes from the choice of grading in this algebra. The grading exactly behaves as if it was counting genus. So we started with a purely algebraic thing, which is an Airy structure, a collection of compatible differential operators, which has a common solution. And we find something which says that the solution can be expressed as a sum over some diagrams which remind of the combinatorics of 2D surfaces and their cutting. So it's in fact not it's not a superficial thing. In fact, we have many examples of Airy structures where this FGN is in fact counting surfaces of genus G with n boundaries in various contexts, where they're counting branch covering of genus G of the Riemann sphere, or counting Gromov-Witten invariants, or computing volumes of moduli spaces of geometric structures attached to surfaces of genus G with n boundaries, etc.
What about construction of isospectral surfaces? Have you here? Is there a connection?
Not directly,
Okay.
because the kind of thing that you do, it's really, so I mean, counting surfaces, that means more or less doing sums of all surfaces. So instead of being interested in one particular type, one special type of surface, it's rather doing the average of all surfaces, so over the moduli space of certain functions, or integrating certain cohomology classes on the moduli space, all these kind of things.
Okay, thank you.
So let me go to now give some examples of Airy structures, because it's a priori not easy to come up with Airy structures, especially, I mean, essentially due to this condition. This is hard to get. You see an ideal, a certain family of compatible differential operators, that's rather hard to exhibit. So there's one way to fulfill this condition is to ask about something much stronger, which is, let's assume that this thing is not here, that this is just forming a Lie algebra of differential operators. In fact, if you look at the algebra of differential operators, is dV, but you look at only the differential operators that have terms of degree at most 2. So it consists of the constant times h bar, x value of the x, so that's in degree 0, it's in degree 2, it's in degree 1. You have xx in degree 2, x h bar dx of the in degree 2, and h bar squared dx squared in degree 2. And this forms a Lie algebra for the brackets, which is the usual commutator of operators rescaled by h bar. And then an easier way to fulfill 2 is to find a Lie algebra morphism. So V would be a Lie algebra. And you can find a morphism to the algebra of differential operators on V of degree at most 2. Then you can, in fact, get something that satisfies 2. And then, well, you need a bit more, another condition with just a linear algebra condition to have the L of V satisfying the degree 1 condition as well. So given the Lie algebra, can we actually find such a thing? So there's classification result due to Hadas and Ruba, which is saying that if V is a simple Lie algebra, then there's only SL2, so A1, SP4, so C2, and SP10, which is C5, admit Airy structures. And then, in fact, up to automorphisms of differential operator that respecting Airy structures, there are only 2 in each case. So there's something non-trivial going on. Instead of, so one can find some time trying to construct some Airy structures, but the more interesting ones are the ones that are really have a relation to geometry. And typically those ones have an infinite dimensional vector space V. So that's what I want to discuss now.
And what about non-semi-simple Lie algebras? Does it have sense, this problem?
Yes. So, but I would say it would be hard to come up with a classification. For example, already if you're semi-simple, you can already find countably many equivalence classes in certain cases. So I would assume the classification is pretty wild.
As usual with non-semi-simple things.
Yes.
And sorry, may I ask you, it is easy to describe the Lie algebra structure of these differential operators of degree at most 2 in terms of
You mean
GLM
this algebra?
in the Yeah, in terms of the dimension of V.
Oh yeah, it's quite easy because you see that's the basis.
Yeah, yeah, I see.
And then you can explicitly commute this. For example, this one commuted with this one, well, that makes a scalar times h bar.
Yeah,
this one you have to commute the two, so you can explicitly write all the commutation relation in these bases.
yeah, I see that, but if dimension is 2 or 3, can you say this is GL3 times GL?
No, it's not.
An
It's
extension of something or something like that.
No, it's not of this type, and the dimension grows pretty fast.
Is it semi-simple?
No, it's
semi-simple. Oops, sorry.
It has center.
I don't think it's semi-simple.
Okay.
No, because of this type of thing, xi xj is going to mix with everybody here. So it's not semi-simple in general.
Okay, thank you.
So now there's one rather general strategy to obtain Airy structures. So the strategy is something that you start with vertex operator algebra. With some free field representation, that is representation in terms of differential operators. And there are already a lot of those, even though it's not everything. But there's already a lot to play with. Then there's a strategy to try to obtain an Airy structure. And then whether either it fails or it succeeds. But you can get that out of the computation. And the reason is that, in fact, when you have this, you have a way to find, I mean, the axiom of vertex operator algebra give you ways to construct interesting ideals. So I'm going to try to explain that for the algebra WGLR. So it's an example of a vertex operator algebra. And I will start with a WGLR at central charge R. So if you think of what is WSL2, that will be the Virasoro algebra. So here, this is a generalization to higher rank. And I prefer to do GLR than SLR because it's slightly simpler to express. Good. So the starting point. So the fact is that at the central chart, there's a nice presentation of this in terms of a Heisenberg algebra. So you first introduce Heisenberg algebra of GLR. But you have the carton of GLR. That means you have some operators, G, A, M, and they commute if A is different from B, and if M plus N is different from 0, and otherwise the commutator is a scalar with an M here. And from this, you make a generating series, GAZ or GAX. So infinite on both sides. Here, A is between 1 and R. M is an integer. And from this, you're going to consider WIX, which is the elementary symmetric polynomial evaluated on J1x, JRX. And you re-expand that in powers of x. The coefficients are called WIM. There's a coefficient of 1 over x to the m plus I. And you look at the algebra of, these are called the modes. You look at the algebra of modes, suitably completed. And this algebra, it doesn't have an explicit presentation for R bigger than 4. So somehow this is the way it's constructed. And there's a lemma, which is due to a work with Bouchard, Chidambaram, Kontsevich, and Noshenko, which tell you that if you have any partition of R, then you can consider the following set of IM, so of indices of these modes, where I belongs to 1 R. And for M, you only take those which are bigger than lambda I, where lambda I is the integer, is the minimum integer. So that when you look at the parts of lambda and you sum up to L, you obtain something bigger or equal to I. So it's another way to code partitions. So it means that you take all m's bigger than something that but may depend on I. And then the WIM for I and m belonging to I lambda satisfy the graded ideal condition. So this is half the work. We tell you that in this abstract setting of VOAs, that is here for WGLR, one can find such ideals. The second part is that this Heisenberg algebra actually can be represented by differential operators. And combining the two together, one can then try to construct Airy structures. So here's one way that will work. You can actually, in that particular case, choose an automorphism of this algebra. So automorphisms for that particular central charge, automorphisms are given by the Weil group. In the case, because it's AR minus 1 more, that's this with 0 to Z, which is flipping the Dinking diagram. So let's choose, I will explain what happens when you just choose that automorphism, the full cycle, 1R. So in that case, you can make the following construction. So you write JA of X as somehow you use the discrete Fourier transform. So use the fact you have an automorphism here of order R to write something like this. So exponential 2i pi j a over R, and then some j tilde j. And you set x equals z to the R. And for this j tilde j, here you put something that looks the Heisenberg, but it can have fractional index. And for this j tilde, you're going to declare it to be So all the j tilde with an integer come up because you have multiplied by r. But depending on the congruence, they show up in different j tilde. So j tilde k is going to be h bar 0 dxk for k positive, 0 for k different from 0, and minus k x minus k plus a constant if k is negative. And so there's a choice of some s, which is positive, which is which constant are you shifting? And these are differential operators on V, which is an infinite dimensional vector spaces, where C here, there's a linear form xk corresponding to it. So it's a differential operator in countably many variables. So to handle this infinite dimensionality, it's possible to do it. I'm not going to discuss that here. You have to work with certain completions of these spaces, but at the end, everything is well defined. So when you do this, if we try to unfold everything, here are the W's. They're obtained from these J's. These J's, they're obtained from the J tilde by a linear transformation. And the J tilde contain differential operators on V. So it makes the WIM as differential operators on V. And very specific one that some we can compute. And so the claim is that for any, so if you take S between 1 and R plus 1, and if you assume that R is plus or minus 1 modulo S, then with this partition, when R is R prime S plus 1, or this partition so here this is R prime plus 1. And this is also R prime plus 1. And it's a partition of R, so it determines everything else in this Young diagram. And so here there's the case R prime S plus S minus 1. If you take WIM for IM in I lambda, that forms an Airy structure. So the relevance from this Airy structure comes from, in fact, a totally different thing, which is the geometry of the moduli space of curves. So I write as a proposal and give some examples where it's known after, and in general, it's still a conjecture, that for any Airy structure coming from a W-algebra, so and also formulated in a bit of a vague way, but at least it should apply to what I explained here. This WGLR at central charge R. There exists a cohomological field theory So what is that? It's a collection of cohomology classes here with C to the R. And I will explain a bit more what does that mean. It's cohomology classes satisfying some specific conditions, such that FGN, so it contains the nth Taylor coefficient of the partition function. So I write here a monomial, and up to some factor, I write CK, so it's some combinatorial factor. It should give the integral over the moduli space of curves of this omega. And here I write, I will explain that notation. Psi1 K1 Psi1 K1 over R integer part psi n Kn over R integer part. And here I write that K is R times this integer part plus the fractional part. And so here, because I had not a cohomology class, but a cohomology class depending on some vector, I take the vector corresponding to those indices bracket of K. So what is a cohomological field theory? This space here, MGN, is a modular operand in topological spaces. This is a compact way of expressing the fact that you can degenerate curve. So it's a moduli space of complex curves. Of genus G with end punctures, which are allowed to have nodal singularities. And there's an extra condition called stability, which I'm not describing here. So the modular operand structure means that we have, for example, these operations. I take a curve of genus G with a certain number of points, which are marked. And some genus G1. And I take another one. And that one has genus G2. And I can glue these two things together to form a curve which is now nodal and has here genus G2 and here genus G1. So in total it is genus G1 plus G2, but except it's the inclusion of this into the boundary of this space. And I have likewise, if I take a curve of genus G minus 1 with n plus 2 points, and I glue the 2 points, I'm going to get a nodal curve of genus G with n punctures. And finally, there's the forgetful map that forgets the last marked point. So this gives operations plus also there's some action of the symmetric group on the puncture. And this gives, so there's relation between these different spaces, and that induces map in cohomology by pulling back or pushing forward. Because this space is compact, so you have Poincare radiality, you can actually push forward cohomology classes. So saying that we have a co-FT means that we have an algebra over this modular operand, which means it's a collection of classes compatible with these gluing maps. So with degenerations, one can say. So I claim that to an Airy structure, one should be able to associate a such family of classes, such that the coefficients of the partition function, which we know are computed by the topological recursion, and are encoding the intersection numbers of this class with psi classes. And the psi classes are certain elements of H2, which can be, which are essentially the first Chern class of the cotangent line when we're at a point C inside the moduli space, so a certain curve. You can look at the cotangent line, that's a complex line. When I vary the curve over the moduli space, it makes a complex line bundle. It has a first Chern class, and that's psi I. All right. So there's a few cases of this proposal, which are, I mean, this is based on some evidence which already exists. The first one is what was Witten conjecture proved by Kontsevich in 91, which said that you can take omega gn, which is the fundamental class. So I'm going to take R equal 2. So C2 is CE1 plus CE2, take a basis. And I take here the fundamental class of MGN bar, and almost by definition, the fundamental class is compatible with degenerations, is respected by the pullback along these maps. So this is a co-FT, cohomological field theory. And in that case, the Airy structure is the case S equals 3, R equal 2 of the theorem. So the theorem was this one. When R equal 2, this is more or less the Virasoro algebra. There's another part, which is Heisenberg, which doesn't really interact here. So more or less, you can think of it as the Virasoro algebra. And what you're saying is that the collection of this intersection number of psi classes on the moduli space of curves, when you put them in generating series, satisfy Virasoro constraint. They're killed by operators and that form the half of the Virasoro algebra. The half being because you only take in that case the M positive here. And this was proved by Kontsevich. I mean, it was the conjecture of Witten. If you look at the case S equal R plus 1, there's something called the Witten R-spin class, which has to do with the moduli space of spin structures. That is curves with punctures, genus G, together with a line bundle. And the R power of the line bundle should be isomorphic to the canonical with certain twists. So omega G and R. And this one is actually rather hard to construct. This was done in the early 2000s by many people, including, Polishuk and Weintraub, for example. We can mention their construction. So it's a complicated object, but it exists. And it has been proved to satisfy W constraints. And that involves the work of many people. But I can say, in particular, Milanov and Bakalov. And is exactly the one which are in this theorem here. So they form an Airy structure. So you can compute that from topological recursion as well. In the other cases, there are some candidates, but I would say this is still open yet. Okay. So now I think remains what, is it 10 minutes or 5 minutes?
Yeah, 10 minutes.
Okay. So I want to describe another class of Airy structure. It's still related to W-algebra, but you use them in a slightly different way. And also you consider general central charge. And I want to explain that you can construct Whittaker vectors. And I will explain for W-GLR. Also, you can also, the story is a bit more in general. So you still look at now W-GLR, but general central charge. In that case, the presentation of the W-algebra is more complicated. It takes the following form. So you still have your Wix, which when you expand in the formal series in X, infinite in both directions. And when you expand them in X, you get the modes. So we'll do here the same expansion. But the formula for Wix is not anymore the elementary symmetric in Heisenberg generators, but it's something a bit more tricky. So there's some alpha 0 that depends specific function of central charge, which I'm not going to explicit here. But the important thing is that there's an h bar to the 1/3. So h bar is also related to the Airy struct to the central charge. So you make it a differential operator in X with coefficients. So when written to the left, R is Wix. And this is the product of the Heisenberg plus d over dx. And now these are differential operators, so they don't commute. So I have to say that this is a product in, say, from left to right in increasing I direction. So for instance, R equal 2, I would have J1x plus, so let's write that delta, nabla, the rescaled differential. So this is the right-hand side. And if I want to write it like the left-hand side, I need to put the derivative to the right. So we have this plus J1x nabla x, J2x nabla x. But when I put the J2x to the left, I had commuted. So in fact, I had to add a nabla x applied to J2x. And that contributes to a constant. So this is our W2, and this is our W1. So in general, there are more derivatives of Heisenberg field that come up in the expression of Wi. And if one sets JA, so the Heisenberg fields, which are h bar dio dxk, sorry. So that's JAK. So now I'm looking at the vector space V, which is infinite dimensional and whose one-dimensional pieces are indexed by A between 1 and R and K positive. So here we have a linear form X, A, K. Here you allow a certain constant. And here you put X, so minus K, X, A minus K for K negative, and that's for K equals 0. So these are differential operators on this vector space V. Therefore, when you compute the W, they're also going to be differential operators on the vector space V. And you want to select only some of these operators so that you have an ideal. So for instance, WIM, I between 1 and R and M positive, forms an ideal. And so that, in fact, with these J's, forms an Airy structure. But it's not interesting because the corresponding partition function is 1. So F equals 0. But there's something more interesting is that you can take this and shift just the mode with I equal R and M equal 1. And I'm going to shift it in a very specific way like this. So lambda is a constant. So here this is true for generic Qs. And here again, Q generic, the value of these 0 modes. And that still forms an Airy structure. Which means that there exists a unique function properly normalized so that WIM, so this is again with I equal 1 R and M positive, which means so there exists a unique F properly normalized such that when you apply WIM to F, you don't get 0. So it's not a highest weight vector. It's rather an eigenvector with an eigenvalue which is non-zero only for I equal R and M equal 1. And this is called a Whittaker vector. It's a generalization of highest weight vectors. So the reason this theorem is, maybe I should mention the fact it's an Airy structure It's in a work with Bouchard, Kontsevich, and Sridharam. But I would say that the hard part of the work is also where the motivation came from, builds on earlier mathematical work. And so it's the fact that when you look at the turns out that the cohomology of the moduli space of instantons. So you can think of it as bundles. Algebraic bundles on P2. And certain issues about how do you, what exactly is this moduli space? How do you compactify it? How do you define the cohomology because it's singular? But all of that can be because of precise incarnation in mathematics. And that admits an action of the W algebra. And the fundamental class which you want to integrate in order to be able to count instantons is the above Whittaker vector. And that is based on several, deep theorems, which actually first were conjectured, maybe not in this formulation, but this originally came from the Aldai, Gayoto, Tachikawa conjecture in physics. And then it's based on theorems by, so there's two works, Molik and Okunkov, and also Breverman, Finkelberg, Nakajima, who are both proving independently a precise version of this. And so what we say here, what we add is that this can actually be computed by topological recursion. And more interestingly, so you can in fact play a bit with this construction using other double algebra, try to use other ideals than the one I used here, and see whether you can still construct Whittaker vectors by exhibiting an Airy structure with this kind of constant shift. What has to be seen is that if you had an Airy structure between these guys, so when you commute two of those guys, it should be in the ideal generated by those, the left ideal. When you start to shift one by a constant, if this guy appeared in the right-hand side of your commutator, then you would totally destroy this property. So it's why it's non-trivial to have Whittaker vectors. What makes it work is that the thing that you can prove that, in fact, just this one, the WR equal RM equal 1, never appear in the commutators of two of those modes. At least you can rewrite it so that on the right, this WR1 never appears. And this is why you still have the ideal condition, and therefore you still have an Airy structure. So you can play with this, and that's what we're doing currently with the same team of people, to construct and maybe classify, if it's possible, that would be the ideal goal, the dream, to classify Whittaker vectors. And then you rather have a concrete hands on them because you can compute with topological recursion what are those vectors. Once you have proved they exist, that means once you have essentially proved in fine ideals where you can shift certain modes. And this should correspond to certain things on the gauge theory side. So this is relevant for n equal to 4-dimensional gauge theories. So that was an overview of the type of geometric applications we consider for these things, and I guess I will stop here. Thank you.
Okay, thank you very much for the great talk. It was a great mix of several subjects, very much. Is there any question? Are there questions, comments? Okay, if not, we thank again and stop the recording.